generators will flow through the transmission lines, all lines. All the lines. So like this, the current is flowing. When the current is flowing through the transmission lines, so the summation of 3 sigma 3 I square R loss is the active power loss, P loss, and similarly sigma 3 I square X is the Q loss. Q loss. So therefore, active power loss and reactive power loss are occurred due to flow of current in the transmission network. So if you supply the current, each current will have. So let us have current I has two components, IP plus JIQ. So IP is the current towards the active power PD, active power demand PD, and this is QD, reactive power demand QD. So if you supply the reactive power here at the load centers, if you have the compensators, this kind of compensators, so this compensator will supply some of the reactive current IQ. So therefore, in the lines, the total current can be decreased due to compensators, isn't it? So thereby you can decrease the IQ with the help of compensators. Isn't it? Not only that, this can be decreased. So due to compensators, it can be decreased. Now the generator has to supply P, and the reactive power component of the generator can be decreased due to compensator. So by placing load points of the power system, different load points of the power system, it is a simple system. If you consider a huge system, many of the generators are there and loads. Many of the generators and loads are connected together. The interconnected network. Okay, you have many connections are there. Many loads and generators are connected together to form an interconnected system. Therefore, at different places, you can have the compensators. This is compensator 1, compensator 2, and so on. Many of the compensators can be connected, C1, C2, etc. So by having that kind of compensators, you can reduce QD, reactive power requirement of the power system. Reactive power requirement of the power system. Thereby, you can also decrease the Q loss, reactive power loss of the system. Not only Q loss, you can also decrease the P loss. P loss can also be decreased. Why? Because the current I has IP plus J IQ. This IQ can be decreased due to compensator. IQ can be decreased due to compensator, and hence the total current of the system can be decreased. When I is decreased, naturally leads to 3I square R loss, sigma 3I square R loss, that is P loss, sigma P loss can be decreased. Not only that, 3I square X loss, sigma Q loss can also be decreased. So this is the advantage of your reactive power compensator in interconnected power system. So let us have this. So in interconnected power system, you have many generators. So like that, you have number of connections are there. Many buses. In fact, you can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 number of buses are there here, among which 3 generators and remaining 7 loads. So therefore, in an interconnected system, if you decrease the current through the all lines by adopting the compensators, by placing the compensators in distinct places, you can decrease the current through the transmission network, and hence overall loss can be minimized and reactive power requirement can be minimized, and so on. Many advantages. Now, before going to discuss further, so you need to understand what is the need of voltage control in power system and what is the relation between voltage control and reactive power compensation. For that, I will use a single line diagram of generator is feeding the load. Generator. There are 2 buses, bus number 1 and 2. So this is the current I. Reactance offered by the line is Jx. V1 is the bus voltage 1, first bus voltage. V2 is the second bus voltage. V2 is second bus voltage. So the power flow through the line is P plus JQ. P plus JQ. The V2 equal to V1 minus IZ drop. Z is the impedance of transmission line. I is the current flowing through the line. V2 is the receiving end voltage or second bus voltage. V1 is the first bus voltage. V1 is the first bus voltage. S is equal to complex power, that is equal to P plus JQ, that is equal to VI conjugate. VI conjugate. And P minus JQ equal to V1 conjugate I. V1 conjugate I. Therefore, I is equal to P minus JQ over V1 conjugate. V1 conjugate equal to V1, it is reference. Let us take the reference phasor. So let us take reference, this is V1. Okay? V1. Now let us substitute I is equal to, so I is equal to P minus JQ by V1. JQ by V1. The expression by substituting that V2 equal to V1 minus I into Z. Z is equal to Jx. I is P minus JQ by V1 into Jx. Now let us separate. Let us separate the terms. V1 P by V1 into Jx plus minus plus and next one Q into X by V1. Q into X by V1 into J square. J square is equal to minus 1. Let us substitute that value so that you will get V1 minus J square, you can have minus 1. So Qx by V1 Q Qx by V1 minus Px by J Px by V1. Px by V1. Okay. Now Qx by V1, so directly you can subtract from the V1. This is Qx by V1. Qx by V1. And the quadrature term minus J Px by V1. Therefore, this is the V2. This is the V2. Therefore, from the phasor diagram, directly you can subtract the Qx by V1. This value, so direct subtraction. Therefore, reactive power variations directly affects the voltage variations. Voltage variations. So V2 directly affects the voltage variations. Is a function of Q. This is the conclusion. From the phasor diagram, you can understand this. If you have any questions here, please raise your questions. Okay. Have you understand? So this is the relation between voltage and reactive power. Voltage and reactive power. Hence, voltage variations depend on reactive power variations. Hence, so therefore you can control the voltage by the use of compensators, Q compensators. Q compensators. This is the conclusion from the previous discussion. Okay. Do you have any questions here? Reactive power. sources and sinks are the power system components. Very first one, synchronous machine. Synchronous machine. Generator is feeding the load Pg plus jQg. Pd plus jQd is the load on the system. Here anyhow excitation control is there. This is V1, V2. So this is Jx. As you are aware of that, P equal to V1, V2 by X sin delta. So what is the Q? Q is also function of voltages. Okay, you can derive that expression if it is required. So when the reactive current can be controlled over excited or under excited modes. So in under excitation mode, it produces reactive power Q, Qg. Generator, right? So and hence you can use the generator as a reactive power source. But it has some limitations. In the capability curve, field current will have its maximum limitation. Maximum limitation, beyond which you cannot generate. So therefore, it has some limitation QG maximum. Already you studied in optimal operation. QG maximum is the limitation for the generator, right? So that you can understand. The second point is the generator will have some reactive power control. That is sometimes during say applications, this field current can be controlled such that the generator may consume the reactive power Q. During light load conditions or no load conditions, you will sense the Ferranti effect. Ferranti effect of the machine. So what is the Ferranti effect? So let us consider normal pi model. IC2 is the current flowing through the receiving end. Admittance y by 2. Here y by 2. IC1. This is IC2 because it is no load. It is operating at no load. And hence this is the current flowing through resistance and reactance of the line. Resistance and reactance of the line. I'll remove this sending end admittance here y by 2 IC2, or slightly I can write IC R and X. So this is the Vs. So this is VR. Okay. Now let us take VR as reference. This is VR. The current IC2 is this one. So you can use. Oh, this is IC. Now IC is flowing through the resistance. Therefore, IC into R is the resistance drop. And IC into X is the reactance drop. And here it is Vs. If you mark here, if you have the arc here, this is the Vs. Therefore, Vs is less than Vr. This is called Ferrand effect. This is called Ferrand effect. During light load, no load, or lightly loaded conditions, we will experience this problem, Ferrand effect. In such kind of situations, we will operate the synchronous generator as a reactive power sink in emergency conditions. So second one is synchronous capacitor or synchronous phase modifier SPM. Here also this is the synchronous motor is taking some load. Here is the excitation control of the synchronous motor. So IF can be controlled. During under excitation operation, it is operating as reactor, and in over excitation mode, it operating at capacitor, in which the capacitor will generate the reactive power Q, and inductor will consume Q. It consumes power. It supplies the reactive power. So therefore, phase modifier will operate both inductor as capacitor. Therefore, it will be used as reactive power source as well as sink. Reactive power sink. Okay, like our synchronous generator. But the synchronous capacitor is designed to operate at no load. So it is not taking any load. So therefore, active power supplied by the synchronous phase modifier is approximately 0. It consumes only its losses, very low amount of losses, P loss. Okay, this is the design of synchronous capacitor or synchronous phase modifier, and its operation under overexcited and underexcited modes, right? So coming to the transmission lines, the transmission lines you can have pi model or T model. Generally, pi model is mostly used in transmission systems in order to reduce the number of nodes of the power system. So therefore, let us have the pi model. Already just now we discussed this. During light load conditions, it provides the reactive power to the system. It is IC2, this is IC1. The total current is IC1 plus IC2. So this is the leading current. So therefore, it supplies the reactive power to the system during lightly loaded condition. Lightly loaded condition, it generates the Q. It supplies the Q to the system. During heavily loaded condition, it consumes the reactive power. It is acting as sink. Here it is source. So therefore, transmission line is also used as sink and source, but the conditions are not in our control. Not in our control, and hence you need to depend upon external compensating devices for the reactive power, not on the transmission lines or generators. So this for this condition, I want to explain one more point. So generally transmission lines are, so you can model approximate model R, X and C. So here the surge impedance loading, the surge impedance of the machine can be defined as, this is the variable load, the sending end voltage Vs, so this is the sending end current Is. The natural impedance of the line is Z equal to root L by C. So here it is L, this is C, LC. So total inductance of the line and total capacitance of the line. So Zn is natural impedance of the line or characteristic impedance of the line, that is equal to square root of root L by C. So when the load is varying, Z load is varying, when it is equal to surge impedance, when ZL, so I will treat it as ZL. ZL equal to Zn, this is corresponding to surge impedance loading. Surge impedance loading. This is very important. When the load is corresponding to surge impedance loading, this is set to natural loading. Natural loading. When load I square omega L is less than V square omega C, then in this condition the line will operate as reactive power source. Reactive power source. And vice versa. When line I square omega L is greater than V square omega C, then it is acting as Q reactive power sink. Reactive power sink. So if you plot the graph like this is distance. So this is the voltage. This is corresponding to surge impedance loading. This is the loading like I square omega L is less than V square omega C. In this condition, it acting as reactive power source. Reactive power source. The other one here, it is, so when I square omega L is less, sorry, I square omega L is greater than V square is greater than V square omega C, then it is acting as reactive power sink. Reactive power sink. Okay. This line corresponding to the surge impedance loading. Surge impedance loading. So this is the source. This is the line. This is the variable load. ZL equal to Zn is the corresponding surge impedance loading. So this is about lines, transmission lines. Now coming to the cables. For the cables, generally the capacitance offered by the cable is far greater than inductance of the cable, and hence cables will operate and acts as Q sources. Cables are reactive power sources. Straight away you can tell that. Cables are reactive power sources. Are everybody following, or any questions? Next one, transformers. If you go for the transformers, so the equivalent circuit of the transformer is R01, X01. So this is V1 and V2. So therefore, when the current is going through the transformer, so you will get I square R loss, P loss, Q loss, P loss, Q loss. P loss is equal to I square R01, Q loss is equal to I square X01. R01 and X01 is the equivalent resistance reactance referred to the primary. And hence it is always Q sink. It always consumes the reactive power, therefore it is reactive power sink transformer. Okay. Next, coming to the synchronous phase modifier or synchronous capacitor, already I explained you. So once again we'll see that synchronous machine, particularly motor. When it is operating as a motor, when it is operating as a motor, so it is not supplying any load. It is operating under no load. Reactive power control is there. This is the reactive power control. So the Q expression, Q is equal to EV. This is and actually back EMF EBV by X cos delta minus V square by X. V square by X. Therefore, V by X is common. EB cos delta minus V. When EB cos delta, EB cos delta, if it is greater than V, then it is acting as source. It is acting as capacitor. If it is less than that, EB cos delta is less than V, then it is acting as sink. So this is about synchronous machine operating as synchronous phase modifier or synchronous condenser. If you draw the graph, this is excitation, y-axis is current IA. So you will have this kind of curve. This is normal excitation, over excitation, under excitation. Now in the over excitation, it is acting as, so this is the capacitor, it is acting as inductor. So for inductor, this operation, it is acting as sink. E cos delta is less than V. Here it is E cos delta is greater than V. It is acting as capacitor. Today I will stop here. Thank you very much. If you have any questions, we'll discuss in the next class, or you can ask me now.